we're really just going to do projectile motion today, so it shouldn't take that long. Remember, like we talked about last time, that the things that you need to remember for projectile motion. Let's see, y'all are all in class, right? You're online. Sorry that we didn't do a quiz this week. I sort of kicked myself in the butt that we didn't, because like the quizzes sort of help you to kick yourself in the butt and get moving. But don't fall behind, because you really need to be up on projectile motion. Like you should be done with it by Monday. And then, because next week's quiz will cover chapter 3 and then sort of the first part of chapter 4. All right? No, projectile motion is the last part of chapter 3. So we just did the first part of chapter 3 this time. Yeah. All right, so in projectile motion, we can have a lot of different scenarios. Like, for example, the simplest one is when I just have one that starts and ends at the same location. And then the velocities here do a couple of things. The x velocity is always constant in the x direction, because ax is equal to 0. It's not accelerating in the x direction. And the y velocity, on the other hand, starts out really big. This is the y component of the velocity. It gets a little smaller. It goes to 0 at the top. It starts going in the negative direction. And then when it reaches the original position at the y equals 0, it has the same velocity but now in the negative direction. All right, so let's work through some problems where we're addressing these, but really we're just working like two separate kinematics problems, and we've already worked both of those, so it's just putting that together. That's not always easy, so let's try working some problems. I pulled up the fall 12 exam, uh, but a lot of the problems look similar. They just sort of have different numbers, slightly different scenarios. So here I kick a soccer ball with an initial velocity of 20 meters per second. Now remember, that's the speed of the ball, not the velocity, because the velocity is actually a vector, so it has a direction attached to it. And so there's the direction. It lands some distance away. We don't know how far away it is, but I could certainly ask that question and you could answer it. And I just want to know, how long does it take to come back to the ground? So this looks like a projectile motion problem, but it's really a lot like a problem that we had on the last test, where I just throw something up in the air and ask how long does it take to come back to where I started. And the only difference here is that I need to know the velocity, the y component of the initial velocity. And so that y component of the initial velocity is, which do we use, our cosine or sine for y component? We use our sine, right? And in this section, the y component will always be sine, the x component will always be cosine. It's really just in chapter 4 when we get dealing with forces in 2 dimensions, where sometimes that changes up. All right, so v naught y is going to be 20 times sine of 30. See, I always forget this. Is this half or 0.86? Yeah, this is half. So this is 10 meters per second. Right, that's the y component of the velocity. And I know that at the top, the velocity in the y direction is equal to 0. I also know that the acceleration in the y direction is negative 10 meters per second squared. So I can do just like we did in the previous section. I can find that time. I just say v at the top. This is v in the y direction at the top, is equal to v naught y plus ay times t at the top. And then I'm just solving for t top, right? Same problem as we had on the test, right? Didn't we have this, something very, very similar to this? Yeah. So vy at the top is 0. That's equal to 10 meters per second minus 10 meters per second squared times t top. Now that tells me that at the top, if I solve for this, I get t equal 1 second. That's t top. That tells me that up here, that t is equal to 1 second. So the answer must be B, right? It's not B, right? It's D. So my time here is 2 seconds because I need to take double the time. I could also ask, what is the range? How would I find the distance to travel out here? And remember, we divide up our velocity into our y component and our x component. Which of those velocities tells us how far it goes in the x direction? The y component or the x component? The x component, right. So we want to find our x component. Um, so this is a separate question, but asking what is the range. Our x component here, Vx, is going to equal to 20 cosine of 30. Let's see, that's 8.6. That's roughly 18 meters per second. All right. And then if I want to know the range, I'll do it up here. I just say x is equal to Vx times t. That's 18 meters per second times 1 second or 2 seconds. I'm going to use 2 seconds. So that means it goes 36 meters. All right. That's the distance from here to here. Similarly, I could also find the distance that it goes in the y direction, where I just plug in for this equation, y is equal to v naught y times t plus 1/2 ay t squared, and just put in the appropriate values here. I would use v naught y, which I've already found to be 10. I would use t. I'll use 1 or 2. I'm going to use 1 second here, and then negative 10, and then 1 second there. And then I could find the height that it travels. So any one of those questions, I could ask you the time in the air, the range, the height, the maximum height. Um, so just carry this on out. This would be 10 meters per second times 1 second plus 1/2 of negative 10 times 1 squared. That's 10 minus 5 is 5 meters. So it goes up a height of 5 meters. It travels 36 meters out. It goes up a height of 5 meters. Okay? You with me? You have very big eyes. Everybody has big eyes. You look like our cat when he's all wound up. Right. Uh-huh. Yeah, let me show you. I'll just write out all the formulae. There are all sort of variations of the same two formulae that we've been using, but let's just sort of write them out. For projectile motion, first of all, we have the components. Right, you'll need to find the components, and Vx, or V naught x rather, is equal to V naught cosine of theta, and V naught y is V naught sine of theta. You'll almost always have to find both of those components. On that previous problem, you didn't need both of them. You just needed V naught y to really solve the problem. But usually you'll need both of those. And then we have the two kinematics equations for both dimensions. So we have the kinematics equations for the x dimension, and then we have the kinematics for the y. Now in the y dimension, it looks more like what we've been seeing. That is that Vy is equal to V naught y plus Ay t. See, that's just like what we had last chapter, except I'm just putting that little y subscript. And then I also have y equals V naught y t plus 1/2 ay t squared. So those are the two equations in the y dimension, and that describes how it moves in the vertical direction. Forget about the horizontal direction for now. Just worry about the motion in the vertical direction. You completely divorce the two dimensions, the x and the y, and you just treat them differently. And then over here, now remember that in the x direction, ax is equal to 0. So it's going to look a lot alike, except I'm just going to leave out any term that has an acceleration in it. So Vx then is equal to V naught x, and it stops right there. That's really just saying the velocity in the x direction doesn't change. That Vx, which is the velocity at any point in time, is equal to the initial velocity in the x direction. So that's really all that's saying. That's not very useful. And then also x is equal to V naught x times t. And I stop right there. I don't write that next term because it's equal to 0. That is for the range, right? So if I want to find the range, that's what I'm using here. The range is just the x displacement. If I want to find the height, I use this. And then if I want to do that little funky thing where I say t top is at t top vy is 0, I have to use this. So if you're really into memorizing formulae, I'm not really, but if you are into that, these are the ones that you need for projectile motion. Okay, are y'all into memorizing formulae? It's not big now right now because we don't have that many, but later we're gonna get a whole bunch. And you know, I'll give you an equation sheet and all that, but really, you just need to know it to even with an equation sheet. Like, don't be too charmed by it. It won't help you a whole lot. But I will give you an equation sheet in chapter 5. Woohoo! Are y'all excited? Yeah. But then you get a whole bunch of formulae, and it's just like, well, what am I gonna do with all this? So, okay. All right. Let's look at some other problems because these things you can sort of see them in different scenarios. These projectile motion problems, each one can be a little bit different. So there's another one in this test that's similar to the one that you'll be doing in the lab next week. Um, oh, this one's easy. Here I have a ball that's rolled horizontally off a table. I give its initial speed, and a stopwatch measures the ball trajectory time to be 0.3 seconds. What is the height of the table? Listen, I always like to draw a picture because it helps me to think about what's going on. So here I have a ball that rolls off the edge of the table, and it follows a path that looks like that. It just falls to the ground. It tells me that the initial speed is 0.24 meters per second. What are the x and y components of this initial speed? What is the direction of the speed right now? Is it in the x direction, the y direction, or somewhere in between? Well, look at the arrow. What is the direction the arrow is pointing? It's in, no, try the other one. It's the x direction, right. So here it's pointed in the, what's that? Oh, it's pointed in a positive x direction. So my v naught is actually my v naught x, because v naught y is equal to 0 in this case. Okay, I know that the time required to get from top to bottom is 0.3 seconds. I know that the acceleration in the y direction is negative 10 meters per second squared. And I just want to know what is the height of the table. Let's see, how am I going to solve this? That, well, let's see. So let's pull up these formulae. I know y, I know t, I know ay, I know v naught x. I also know v naught y. Which of these do you think I could use, or some combination of them could I use in order to find the, was it the height of the table I was looking for? First of all, what am I looking for? Which of the variables? The height of the table is what? Is y, right? I'm looking for this. So I know that eventually I'm going to have to use this formula. So let's just look at it and see if we know everything. V naught y? Well, that's 0, right? Because v naught x is the only initial velocity. So this whole term goes away. Do I know ay? Yeah. And I know t too, right? Yeah, so this is really easy. I just use that and I'm just plugging in the right numbers. So I just say y is equal to v naught y times t plus 1/2 ay t squared. And then I can cancel out some stuff. I can get rid of this. And then I just say y is equal to 1/2 of ay, which is negative 10, times t squared, which is 0.3 squared. And that'll be the answer. 5 times 0.3 squared. 0.4. I got 0.45, but I was using 10 instead of 9.8. So the answer is 0.44. That's using 9.8, by the way, if you're worried about that. I use 9.8 there. But on the test, you'll have 10. By the way, our test isn't that far away. It's September 30th, which is, what's today, the 10th? Is today the 10th? Yeah, so it's just a few weeks away. All right. Oh yeah, it should be negative, but I'm just asking for the height of the table. So the negative, like I'm asking how high a table is, the negative doesn't mean anything. Now you're right, you'll get an answer because you're letting this be 0, and the ground is below 0, so it'll be a negative direction. Your displacement is negative. Yeah, right. Good question. So my V naught is in this direction. My initial velocity, it comes off that table. It's not at any angle. It's just coming straight off. So the initial velocity is completely in the x direction. There is no velocity in the y direction initially. Now, as soon as it comes off the table, right, it does start picking up a y velocity that increases with time. You know, another question I could ask, and I have asked this on test, can I erase this? I could ask, what is, this is a little more complicated, but not a lot more. What is the final speed? All right, so I know that down here at the bottom that I have a velocity in the y direction, and I also have a velocity in the x direction. Now the velocity in the x direction is easy. I know that. That's 0.24 meters per second because that's what it was initially, and I know that it doesn't change. You with me on this? So now I need to find the velocity in the y direction, and then I'll combine those two vectors. It'll be the x and y components of the vectors, and then I can find the velocity, the speed of the object. So in order to do that, I say Vy is V naught y plus Ay times t. That's 0 plus negative 10 times t, which is 0.3 seconds. So it's negative 3 meters per second. So I have 0.24 in this direction and negative 3 in this direction. And then if I want to find the actual speed, it would be the square root of Vx squared plus Vy squared, which is going to be 0.24 squared plus 3 squared. The 0.24 doesn't really contribute much, so it's just going to be about 3 meters per second. A little more than 3 meters per second. Okay? So as you go through the old test, which I really recommend that you do because every problem is a little bit different, but they're all sort of on the same framework, but it's just what you have, the information that you have, and what you're looking for will be slightly different. Yeah. You want to take a look at it? Okay. Yeah, let me pull it up. Chapter 3, right? Yeah, you see, this is a very similar problem, except you just have different information. You don't have the time here. So anytime you come to a projectile motion problem and you don't have a time, you immediately need to start looking around, looking for the time, trying to figure out how you're going to find the time. And almost always you're going to use the y motion, the vertical motion in order to find the time. Sometimes you can have the right information to use the x motion to find the time, but almost always you're going to use the y motion. So I wanted to actually look for a problem like this, so this is a good one. Here I have a similar situation. I have an object that comes off like that. In this case, it's a car. I know that it traveled a distance of 20 meters, and I know that the height here is 100 meters, and I want to know how fast it was going when it went over the edge. By the way, this is going to be almost just like the lab that y'all do next week. Are you in the lab? You're not in the lab, are you? Okay, so I want to find the time. Let's just write down what I know. I know that y is equal to negative 100 meters, and I know that x is 20 meters. I know that v naught y is equal to 0, just like the previous problem, because it comes off at a at a horizontal direction. And I know that v naught x is, well, I don't know what v naught x is. I also don't know what t is. All right, but I want to find t. Remember what I said? You almost always use the what motion to find the time, the y motion. So you're just going to treat this like an object that's dropping from 100 meters, and then you'll be able to find the time. All right, let me show you. you're going to say that y is equal to v naught y times t plus 1/2 ayt squared. Now fortunately, v naught y goes away because v naught y is equal to 0. So that whole term goes away. It's good for you that it goes away because otherwise you'd have to use the quadratic. And I've never seen a student get the quadratic formula right on the first try. Like I usually get it wrong on the first try too. It's just all those A's, B's, and C's, and you got negatives and you got positives. Ugh, it's a mess, right? So anyway, that goes away. Do you get it right every time? Oh, okay. Oh, you know the song. I didn't know there was a song. All right. So anyway, it's an easy problem because I have to solve the quadratic. So I have negative 100 equals 1/2 of negative 10 times t squared. Uh, that is 100 divided by 20. I mean, sorry, 100 divided by 5. So it's the square root of 20 is t. That's 4.5 seconds. All right. Now, once I find I just want to know how fast it was going. Now I can do this in a couple of different ways. Probably the easiest way to do this, since I know the range, I can say that x is equal to v naught x times t, which I think this is the only way to do it. Um, x is v naught x times t, and so I know that x is 20 meters, v naught x I don't know, and I know that t is 4.5 seconds. So here, instead of finding the range, I'm working backwards from the range to find the velocity in the x direction. And so that's 20 over 4.5. That's 4.4 meters per second. And that's the answer. That's a good test question. I mean, sometimes the homework problems are a little more difficult than you see on the test, but not this. This is a good test question. They're all good practice for the test, but this one particularly could be a good test question. Yeah, Taylor. Well, v naught x is equal to the initial velocity. On the previous one, we had the initial velocity, and we said that is the v naught x. But this one's a little bit different because you don't have the initial velocity. And instead, you have a different set of information, right? In the previous one, we knew how fast it was going. And I forget, we had we had the time and some other different things. But here, all we had were just the x and y displacements. And so you had to approach the problem a little bit differently. You know, this might seem really foreign to you right now, but it's going to get easier as time goes along because you'll just sort of get a feel for how to approach the problems when you sit down to them, uh, both sort of reading the language and getting the language right, but then also mathematically how to approach them. Do you believe me? Or do you think it's already easy? It's already easy? No? Okay. Let's look at some others. Can I clear this one? Does that make a little more sense to you? Okay. It's a good one to make sense to you because it's a good test question. All of these are good test questions, but and don't forget the test is coming up. It's just like 20 days away. We just need a big countdown timer like on the website. I'll look into that. Okay, I think that was all the projectile motion on this one. What is this, fall 12? Let's look at fall 13. Usually these are going to come in exam 2 for y'all. Oh, but not in fall 13. It was exam 1. Well, we were chopping that semester. Blah, blah, blah. Is this different? No, this is largely the same. No, this is a little bit different than what we had before. Yeah, so another variation on that same problem, but again, you have a different set of information. Because here we don't have t, but we have y and we have vx, right? Isn't this different or is it the same? Do you know? It does have x motion. Well, we don't have the time. Yeah, so let's go through it. Here, I just want to know, if you're in a plane, and you drop a bomb or whatever, like if I have something that I want to drop from this plane, as you know, it doesn't just fall straight down, right? You ever been in a plane when they drop a bomb? No? Okay. Well, if you had, you would know that they have to plan their trajectory so that, I mean, some bombs have actually propulsion on them, right? They have propellers and they move on their own. But a lot of them are just inactive, and you drop them, and depending on the speed that they have, they'll follow a certain path, a projectile path, right? It drops with a velocity equal to the plane. And so if this plane is flying at about 42 meters per second, about 100 miles an hour, uh, and it's a half a kilometer from its target. No, I'm sorry, it's a half a kilometer from the ground. They want to know how far away from the target should they release the bomb. So let's see, reading this, I know that y is equal to negative 0.5 kilometers, but I'm so darn good at doing unit conversions now, I know that that's immediately what? 50? Is it 50 meters? 5 meters? 500 meters? It's 500 meters, right? All right, a half kilometer is 500 meters, and I know that the initial speed is 42 meters per second. Is that x, y, or just some in between? That's my x motion, right? So I'm going to put a v naught x. I also know that v naught y is equal to 0 then. Um, I know a y is negative 10 second squared, and I want to know what is the distance d, which is also the distance x. What is the x displacement? Now, from those equations that I put up on the board earlier, I know that in order to find x, I need to know v naught x, which fortunately I know, and I also need to know t, which I do not know at this time. So your big order here is to find t. How are you going to find t, you think? That whole y thing, right, which is often what you'll do to find t. Sometimes it's not, but often that's the way that you'll find t, where you do this whole y thing, v naught y times t plus 1 half ayt squared. This goes away. Y is negative 500 equals 1 half of negative 10 t squared. That's 500 over 5, that's 100. T is the root of 100, that's 10 seconds. So this object, if you were just to drop it from 500 meters, would take 10 seconds to fall. That means in 10 seconds, it needs to go from here to here. All right, so I want to know how fast or how far will it go in 10 seconds. And so I can take this, plug it in here, and I got 42 times 10, 420. So B is the right answer. Right, that is the range, 420. All right, Maria? Okay, I know. Yeah, me too. But let's see if there's another one that's similar to that. Can I clear this? So what she's saying is there are a couple different variations, right? You have like this one, which is just sort of like half the motion, and then you have that where you have the full range of motion. And I'll look for one that is somewhere in between. I don't know if there's one like that here. No, there's not one here. Let's pull up another one. That was fall 13. Let's look at fall 11. This is fall 11. Exam 1. Okay, this one's very similar to what we wrote before. this one, number 8. Is this okay? This is similar to the one we worked before, but I think it's always good to see extra problems. So here, you should be able to work this number 8 all on your own now. This is fall 14. Actually, I think this is in the back of your book if you want to follow along there. It's exam 2. A large cannon is fired from ground level over level ground at an angle of 30 degrees above the horizontal. The muzzle speed is 1,000 meters per second. It will travel what horizontal distance? All right, so I'm going to draw a little picture over here. Something like this. All right. I want to know this distance. So I'm looking for x. And I know that the speed here is 1,000 meters per second. And I know that this angle is 30 degrees. I further know that v in the y direction is equal to 0 at that point. What's my first thing to do? Right, you want to find your components first. Almost always you want to find your components. I want to find v naught x and v naught y. I know I'm going to need v naught x in order to find the range, and I'm going to need v naught y in order to find the time. So let's just go ahead and do both of them. That's going to be 1,000 cosine of 30 and 1,000 sine of 30. See, this is 500, and this is 860. And then after that, I have those. My next step will be to find the what? The time, right? I want to find the time. In order to do that, I say, well, Vy top is equal to V naught y plus AYT. Vy top is 0. V naught y is 500. I've already found that. Minus 10 meters per second squared times T top. So that's T top is negative 500 over 10. So that's 50 seconds. It takes 50 seconds to get from here all the way up to here. May seem like a long time, but they're shooting at 1,000 meters per second. That's hella fast. So it takes a long time to get to the top of its trajectory. Okay, so that's the second step. And then the final step, I'm going to do what? Oh, because I know that the velocity up here at the top is equal to 0. So I can put it in there. And then I can solve this equation to find this T top. Right, so I know that up here, 50 seconds have elapsed at this point. And I also know that because this is symmetrical motion, that over here, 100 seconds has elapsed. So now you were about to say the final step is what? Right, T total, I'll call it now. All right, so that's V naught X is, we found it up here, 860. And I just multiply that times the time, which is now 100 seconds, not 50, but 100. So that's 860 times 100, 86,000, which is, let's see, it's in kilometers. So how many kilometers is 86,000 meters? 86, yeah. D is the right answer. On this, students then had to use 9.8, so the answer comes out a little bit different. All right. Right. As long as it comes back to the same position, here to here, I get half the time on this side and half the time on this side because it's symmetrical. Um, can I go on from here? Let me try to think of a question where I know there are some in the test, but I don't know exactly where they are. where you have something that comes off like this. This one's quite a bit more difficult. Let's say that I have this sort of scenario. Let's say that it's, I don't know, 10 meters off the ground. Let's say that it travels 20 meters. Oh, that's not that more difficult. Let's say that V naught, say this angle is 30 degrees. Now we're at V naught. Can we solve that pretty easily? Let me just double check. Now let's instead, let's not give you this. Let's say we don't know what that is. Let's say that V naught is equal to 5 meters per second. This will work, right? Will this work? You don't know, do you? I don't know. How can you know? Well, I don't know. I'm thinking. I'm sorry. I'm just thinking out loud here. I'm trying to make this up on the fly. Um, no, let me find a problem right quick. Hold on. I know that I have some somewhere. Is this 2014? Sorry, just a second. That's 2012. We already did that one, huh? I'm not sure. Let's look at some of these conceptual problems, okay? And we'll sort of focus on that for a little bit, because those can be difficult all on their own. All right. How about this one? I like to ask this question. Which of these projectiles remains in the air for the longest amount of time? Is it A, B, or C? Think about what in a projectile defines how long it's in the air. Which of these, A, B, or C? They can have different speeds, or we don't really know what the speed is. Which one's in the air for the longest amount of time? Which has the longest hang time as it is? B, you would think it would be B, right? But it's not B. The time that it's in the air is always set by the y motion. So if it goes up higher, it's in the air for longer, right? This thing's in the air for less amount of time than this thing. If it goes higher, it's in the air for a longer amount of time. So which one is in the air for the longer amount of time? A is in the air for the longer amount of time. Which one has a greater, no, never mind, that's not necessarily true. A is A is in the air for the longer amount of time because it goes up higher. Um, how about this one? A cart is being pulled along a horizontal track by an external force and it's accelerating. A cannon on the cart fires straight upwards. After it is fired, what happens to the ball? Does the ball fall into the cart? Does it fall behind the cart? Or does it depend on the initial velocity of the cannonball? Or does it fall in front of the cart? On the cart? Behind the cart? All right, you can think about this, right? If I'm walking along at a constant velocity and I throw this thing up, it's going to go up, and then it's going to come back down again. Right? Because it follows a projectile path. It's kind of like the airplane. When an airplane drops a bomb, you always see the bomb directly underneath the airplane. You'll follow what I'm saying? Like if I have a plane here and it drops a bomb, the bomb's going to follow this path, but the plane is going to follow this path, so that at every point it will see the bomb right underneath it. And this is sort of a similar thing where if I take this and I throw it up, moving at a constant speed, I will always be directly underneath the object because I have a velocity in the x direction, and this also has that same velocity, just like the bomb. But if I start speeding up, what's going to happen to this after I let it go? Yeah, this is harder to do. So, right, like if I speed up, it's going to fall behind me. Okay. It is accelerating, right. So the answer is that it falls behind the cart. All right. If it was constant, right, if it was constant, if I was just moving along like this, it would fall in the cart. That's a lot like the plane. It would know. Just because you're going slow doesn't mean it's going to go ahead of you. In fact, the only way for it to go ahead of you is if you're slowing down, right? I can't do this, but if I'm going really fast and as soon as I let it go and I slow down, then it will go ahead. But that would be sort of like the plane slowing down as soon as it drops the bomb. And this thing, like if this is moving at 10 meters per second or 100 meters per second or whatever, this is also moving at 10 meters per second. And if the plane does slow down, then yeah, the bomb will keep going forward. Uh, you followed? All right. I like to ask those kinds of questions. Um, ooh, this is a good one. Hardly anybody got number 11 right. Let's see how y'all do. So here I have a projectile. Yeah, this is fall 14. It's in the back of your book. Um, I have this. It travels along. In each interval here, m between n and o is an equal time t. All right, so I have a time t that goes through here, a time t that goes here, and a time t that goes through here. Now, if the distance m is 2 meters, so this distance is 2 meters, what is the distance n and what is the distance o? I want to know this distance and this distance. Now remember, we're looking at what displacement, the x or the y displacement? I'm looking at the y displacement. So y is equal to v naught y t plus 1/2 ayt squared. Now v naught is 0 in this case. All right, so what I'm looking at here is this expression, that y is equal to 1/2 ayt squared. Okay? Now what happens if I double the time? So here at time t, I have a distance of 2 meters. Here at time 2t, what is going to be my distance? It's going to be what? Let's see. So if I double this, I quadruple the distance. Yeah, so you're right. So it's going to be 8 meters, right? And then over here, what happens to my time? How much more is it? I have 1t, 2t, 3t. So here my time is tripled. So what is going to be my new distance? 18 is right. Right, because I have 3. If I triple my time here, that means I get a factor of 9 over here. It was 2 meters, so now it's 18 meters. So the right answer then is D. 8 meters. I have 2 meters here, 8 meters here. It's 2 squared more. And here I have 18 meters. It's 3 squared more. You follow me on this? It's a quadratic relationship. So if I double the time, I quadruple the distance. If I triple the time, I increase the distance by a factor of 9. What's that called? Nintuple, I guess. I don't know. All right. You with me? Yeah. All right. Let's try a couple more. Let's look. We'll see these again either as you're going through the online test or in class. Um, how do I work these? A bullet shot horizontally from a gun. Which of those is it? It's talking about two different bullets here. I have one that I just drop and it goes down, and then another that I shoot. And I want to know what is what do they do? Does one of them strike the ground first? Right, I shoot a gun right here. Bang. As soon as I shoot it, I drop a bullet. At the same instant, I drop a bullet. So I have a bullet going that direction, and I have a bullet going that direction. Which one hits the ground first? You would think this one would hit first, right? But they actually hit at the exact same time because they both fall with the same acceleration. They both fall, and I sort of misdrew this picture a little bit because it doesn't have a velocity in the y direction, but they both fall with the same acceleration equal to -10. Can sort of show you this. I have a thing upstairs that shows it, but I have these two things. I'm going to drop them at the same time, but the only difference is I'm going to sort of kick this one off to the side. Right, so that's like the bullet, and they both hit at the same time because they're both falling at the same rate. Just a couple more minutes, y'all. Let's do a couple more of these questions. That's a real life situation. Okay. We're not going to shoot anybody. Okay. It did work. I didn't see that episode. All right. Actually, I just saw my first Mythbusters this weekend. It was pretty good. All right. Which of these plots represents the y component of the velocity for an object launched from the ground and returns to the same y position? Listen, y'all should be good at this by now. Which one is it? Is it B? No, this is one where I have one that goes from this direction and it goes up. Remember, I drew the y velocity. Doesn't look right, does it? So what's the answer? E is the right answer. Right. Because you're right, it should look a lot like B, but it should look the other direction. Yeah. Nobody ever answers E, do they? But, all right. It's okay, we're going to wrap up. Unless you have specific questions? Projectile motion. Man, it's not hard. It's not hard at all. It's right. But everybody does projectile motion. Listen, our pastor, he coaches soccer, right? And he says that a 4-year-old does projectile motion. Anytime you shoot a soccer ball into the but you know, you get a feel for it. You don't think about the math of it, but you know projectile motion. It's gonna be fine. We'll spend in the in class section. We'll spend a little more time on it. We'll do the concept test and work a few more questions. But on Friday, we'll probably wrap it up Friday, and then move on to chapter 4 on Monday. Yeah. On the next test, 3B, 4, and 5 probably. Some of 5, probably all. 5 is really short. Chapter 4 is kind of the longest chapter. So, you know, 2 to 3 days on that chapter. 3 days, maybe. This is the hardest test. All semester, this is the hardest test. But that's an A. Basically an A. All right. Exam grades don't matter, right? It's just the last grade that we're shooting for. And listen, let me tell you something. I won't say the student's name, but a student wrote me and said, "Listen, I'm sort of freaking out because I didn't do all my exam because I made a 50 something or whatever on my exam." And I went and I ran the numbers, and if this student makes a 90% here on out, they'll get an A in the class. Even though they made a 50 something on the first exam, if they make 90% here on out on the 3 exams on the final and the quizzes, they'll get an A in the class. You get that? What that's saying? I don't. Yeah, it's not that bad. All right. There's a lot of points in this class. You can do well. All right.